So our data are random sample of size n from population interest. Observations from the population have normal distribution with mean, mu, standard deviation, sigma. In practice, it is enough that the distribution be single-peaked, symmetric, and the sample is very small, unless the sample is very small. But this is what we've been talking about. Why would I actually know sigma if I don't know mu? That doesn't seem reasonable, and it's usually not. So now we have to talk about what happens when we don't know sigma. Well, if we don't know sigma, what's our best guess for what sigma would be? S. So we're going to use S instead. So now is where you start filling in stuff. We are going to, I think this actually has X bar on yours. Switch that over. We estimate the standard deviation of X bar. So what did we use as the standard deviation of X bar? Like the whole equation for sigma of X bar. What is the equation for sigma of X bar?
Sigma over square root n.
All right, so we're going to estimate all of that instead as what? S over square root n. So this over here is the standard deviation of that statistic. If I have to put in a statistic in that equation, I had to plug in S instead of sigma. There is going to be a little bit of error, right? This is called the standard error as opposed to standard deviation. And that applies for the next couple chapters. Anytime we're dealing with that standard deviation section and we have to plug in a statistic instead of a parameter, it becomes standard error, which means we know there's going to be a little bit of error there. So when we substitute using standard error instead of standard deviation, the statistic does not have a, and I didn't leave you much room for this, a standard normal, which is Z, distribution. You just write Z distribution if you want to. It instead has a T distribution. And what a T essentially does is account for the fact that there is error. Anytime we use standard error, there is going to be error. And the T accounts for that. So the T is a little bit more conservative.
So we're using S and T when we don't know.
Yes, so all those connect. So if you don't know sigma, you use S. If you use S, you use T. Yes.
And if you know sigma, then you use
Z.
Mm-hmm. And sigma.
Mm-hmm. So my Z equals equation, if I'm plugging in numbers, my Z equals equation, in general, what goes on top? So when we were doing this yesterday, homework, we plugged in what right here? Which was what? And we did a confidence interval, so it's a little bit different. But then we would do minus what? So this is value minus mean. So what is our mean overall? And what did we use as standard deviation when we were dealing with a sample or a group? Over, right? So if we use this idea, and we're still using X bar minus mu, but it's S over square root n. This basically, I don't love that I wrote it that way. This just means when we're using S and we're using T, it has a T distribution with degrees of freedom, which is something we said that is on that sheet, but we didn't talk about it yet. So what happens here is, how many variables did I have to estimate in this equation right here? I'm solving for this. I'm not plugging anything in. So how many numbers did I have to plug in that I estimated? We had to estimate what sigma was by using S, right? So we estimated one variable, one parameter.
How do we find what sigma is by using S?
We estimate what sigma is by using S. We don't know what sigma is, so the closest guess we have is S. So basically, what you need to know is there's error. So to account for error, we're using n minus 1 instead of n in the t distribution. And then I'm in that gap right below. Yours doesn't say that. Draw a curve right there. That is my z curve. Have we ever talked about z changing? But has our z curve changed? No. We've dealt with it for 3 chapters now, and we've never talked about z changing. Z is always the exact same. Mine doesn't look very symmetrical there, but a t actually changes. So a t changes depending on what your sample size is. Alright, so let's say I'm going to call this one a t with degrees of freedom of 10. If my degrees of freedom was 10, what was my sample size? 11, because n minus 1 is degrees of freedom. So we were a little bit more conservative here. So instead of me being really sure that a lot of them were right in the middle, and it's really, really unlikely that it gets out that far, we're a little bit more conservative in saying, okay, it can happen that it gets that far away. A little bit more likely that it gets that far away. So what do you notice about t versus z in the tail? T is what in the tail? T is taller in the tails, higher in the tails. What about in the middle? T is shorter than z in the tail, or in the middle. What's the whole area under a z curve? What? 1. So if I make it higher up here, can it be higher in the middle too? No. Now, if I switch and use degrees of freedom of 20, I'm going to be somewhere in between. So I'm going to be somewhere in between out here, and I'm going to be somewhere in between through here. I didn't say much yet. I just said it's in between out here and in between in the middle.
Wait, what?
Green is between black and blue here. Green is between black and blue in the middle.
What do you make it green?
Yeah, T of degrees of freedom of 20.
I thought purple.
That's a degrees of freedom of 10. So T is a family of curves. It's a whole bunch of curves. So to go from my blue to my green.
Are we supposed to have, what's written up at the top?
No, that was a reminder to myself of what I was doing here. When I go from blue to green, my sample size is doing what? Increasing. As my sample size increases, my T does what? It gets closer to a Z, which means taller in the middle and shorter on the outsides. So as your sample size increases, your T gets closer and closer to your Z. So why does that make sense with the purple sheet in front of you? Because the infinity is Z-score. So as my sample size gets bigger and bigger, as it gets to infinity, it actually becomes a Z. Now, I used to do this on a test or quiz or something and have people sketch this. One weird side note is I'd always have people turn in something like this. It can't go back up on the ends. So they weren't thinking about what they were doing. They were thinking about making sure they're like in between and stuff. But definitely don't make your curve go back up on the ends. So it's more conservative. So T is not as tall in the middle, but it is taller on the outside than a Z. As my sample size increases, my T gets closer and closer to a Z. Because we always talk about the bigger your sample size, the more accurate you are. Well, the bigger your sample size, the closer you are to that Z distribution. All right, so we're just going to practice actually using the purple sheet, blue sheet, whatever you want to call it. So on your sheet, whatever color sheet you want to call it, we've got on the left side, now this is the one that you use, so you can't write anything on here other than today. What's on the left side?
Yeah.
What's the degrees of freedom. So the first line is for degrees of freedom of 1. So that's actually with a sample size of what? 2. So you have to go back and forth between sample size and degrees of freedom. That should be very hard. On the bottom is confidence levels. On the top is tail probabilities. And we talked about the relationship between confidence level and tail probability on Friday. All right, so just reading the chart itself, a T distribution, I'm just going to do a curve real quick, with 5 degrees of freedom, which means my N was 6, but I need to know degrees of freedom to use this. The area to the right was 0.05. So I'm at tail probability of 0.05, down to degrees of freedom of 5, and I get what?
2.1.
So T star would be 2.015. What about, so now I'm saying to the left, well, if 0.99 is shaded to the left, that really leaves me with what on the right? 0100. My tail probability is 0.01. With degrees of freedom of 21, what is my T there?
20.
What's my T there? What? 2.518. So all we're doing here is making sure we can read the table. Finish out C through G really quickly. Like, we found that this was your right tail, and your purple sheet in front of you is right tail, so you just go to the top of 0.01.
I would have to find 0.01 and then do it in 21. Okay, you have to look at your right. Can I write that on my purple sheet? It's right tail.
You can just write your picture up here. C first. What do I do with this? That's my what?
That's your end.
So I actually need to use that to find my what?
Degree freedom 14.
So sometimes it gives you degrees freedom, sometimes it gives you sample size. A problem's actually going to give you sample size. A through D are just reading the table in general. E through G are going to be how we actually see it for a problem for this chapter.
Where do you get 0.688?
You're looking up that is your 0.25, your probability with degrees of freedom of 19.
Probably.
0.25, not 0.025.
I'm literally looking at it.
So I'm going to switch to the next slide. Your C is 2.145. Your D should be 0.688. So D should be pretty easy. You just find degrees of freedom, and then your confidence levels are at the bottom, which is how it's going to be this chapter. And I could draw it out if I wanted to, but they'd all look the same because you'd have percent in the middle with a number drawn. And you should have gotten those as your T-star values.
Yeah, how do you do this part?
Your percent on the bottom. You just have to find degrees of freedom.
So we're just doing it the other way. So now we have
Look at the bottom of 7, which is what we're going to do this chapter. I wish I would have done one like this, but what if my sample size is 45? If my sample size is 45, what's my degrees of freedom? 44. How does that become an issue? 44 is not on the table. So if your degrees of freedom is not on the table, you have to use the highest degrees of freedom available that is still less than the one you're looking for. Because the higher your sample size gets, the more accurate you get. So you don't want to be more accurate than the number you're using. So you have to be conservative. So we would have, if we were using the one of a sample size of 45, using this sheet, we would have to go to degrees of freedom of what? Of 40. Ideally, and don't think about these together, but ideally, what kind of confidence do we want? If you're giving someone information, what kind of confidence do you want? So we want high confidence. And then again, don't necessarily think about these connected. Well, what kind of margin of error would we want? Because we don't want to give them a number that spans from 10 degrees to 100 degrees.
But then didn't we say our margin of error?
Right. That's why I said don't be wrong together.
Okay.
Because as your margin of error decreases, your confidence level increases, your margin of error is also going to increase. So you can't do them together. Ideally, in each scenario, we're looking for something with high confidence. We're looking for something with low margin of error, but we're going to make adjustments with it. All right, similarities and differences between the standard normal curve, which is Z, and a T distribution curve. So we already started talking about a little bit of this. With the curves that we drew right there. So the first curve that I started with was the Z curve. And what did I say about the Z curve?
That is sample size increases, C gets closer.
But what happens with just Z itself? What do I know about just Z itself? How many Z's did I draw on there? How many Z's did I draw on there? Why did I only draw one Z? It does not change, but T does change based on the sample size. So what's similar about them? They're both approximately normal. I don't want to write that, but you're still using a normal approximation for both. Yes. What else? What about the curve themselves?
Both bell-shaped.
They're both bell-shaped. What else? You could say unimodal, but I think bell-shaped is just a more descriptive way to say unimodal. What did we talk about with area under the curve? They are both density curves, so they apply to probability, which means the area under the whole curve is 1. Alright, they tell me one place they were different.
T can change.
Alright, so T can change, based on what? While Z always stays the same. Where are they different in the curves themselves?
Just below.
Z is taller and the but T is
Okay, so
taller.
Z is taller where?
The middle. But T is taller than wing.
And I'll just do it as two separate ones. So in the middle, then Z, then T. But T is taller where?
In the
Where do we, there's something that's on there.
tails. Sorry,
Tails, yeah.
I'm saying wings.
And then I don't know where to write this. As N increases, what? T approaches or gets closer to,
Z.
but I didn't like writing that as similarities or differences. I wasn't really sure where that goes. Oh, that's